Good day, everyone. Welcome to this case study presentation on building a digital voting system using logic gates. In this presentation, we will walk through the complete process of designing a simple but functional electronic voting circuit. This is a real-world application of logic circuits, specifically how basic AND and OR gates can be combined to create a majority voting system. By the end of this presentation, you will understand how to identify the inputs and output of a problem, construct a truth table, derive a Boolean expression, design the logic circuit, and verify that it works correctly. Let's begin. Let's start with the problem. A small community wants to implement a digital voting system to automate and secure their election process. The system has 3 voting stations: Station A, Station B, and Station C. Now, here is the key rule. If at least 2 out of the 3 stations vote yes, then the overall election result is yes. On the other hand, if fewer than 2 stations vote yes, meaning 0 or only 1 station votes yes, then the result is no. This rule is called a majority function. The output simply follows whatever the majority of the inputs decide. Think of it as a simple democratic process. The majority wins. So our task is to design a digital logic circuit that implements this majority rule automatically. Now let's define the system clearly. Our circuit has 3 inputs and 1 output. The 3 inputs are vote A, representing Station A's vote, vote B, representing Station B's vote, and vote C, representing Station C's vote. Each input is a binary value. 0 means the station votes no, and 1 means the station votes yes. The single output is the result, which represents the final election outcome. If the result is 1, the election outcome is yes. If the result is 0, the outcome is no. On the right side of the slide, you can see a system block diagram. It shows the 3 voting stations feeding their signals into a logic circuit, which processes them and produces the final result. This gives us a high-level picture of what we need to build. This is the truth table, one of the most important steps in digital logic design. Since we have 3 inputs, each of which can be either 0 or 1, there are 2 to the power of 3, which equals 8 possible input combinations. The truth table lists every single one of them, along with the expected output. Let me walk you through the key rows. When all 3 stations vote no, 0, 0, 0, the result is obviously 0, no. When only 1 station votes yes, like 0, 0, 1, or 0, 1, 0, or 1, 0, 0, the result is still 0 because 1 vote is not a majority. Now here is where it gets interesting. When 2 stations vote yes, for example, 0, 1, 1, or 1, 0, 1, or 1, 1, 0, the result becomes 1, which means yes. 2 out of 3 is a majority. And of course, when all 3 vote yes, 1, 1, 1, the result is also yes. Looking at the key observations on the right, the result equals 1 whenever at least 2 inputs are 1. Out of 8 possible combinations, exactly 4 produce a yes result. This confirms we are dealing with a majority voting function. Now we derive the Boolean expression from the truth table. We look at the rows where the result equals 1. These are rows 4, 6, 7, and 8. From row 4, where A is 0, B is 1, and C is 1, we get the term B and C. From row 6, where A is 1, B is 0, and C is 1, we get A and C. From row 7, where A is 1, B is 1, and C is 0, we get A and B. Row 8, where all inputs are 1, is already covered by the previous 3 terms. Now we combine these 3 terms using the OR operation, which gives us the final simplified Boolean expression. Result equals A and B or A and C or B and C. In plain English, this means the result is yes if both A and B vote yes, or if both A and C vote yes, or if both B and C vote yes. Any pair of stations agreeing on yes is enough to produce a majority. The dot symbol represents and the plus symbol represents OR. Here is the logic circuit diagram that implements our Boolean expression. On the left side, you can see the 3 inputs, vote A, vote B, and vote C. Notice that each input branches out to connect to 2 different AND gates because each input participates in 2 of the 3 AND operations. In the center, we have 3 AND gates. The first AND gate receives vote A and vote B, and it computes A and B. The second AND gate receives vote A and vote C, computing A and C. The third AND gate receives vote B and vote C, computing B and C. All 3 AND gate outputs then connect to a single OR gate on the right side of the diagram. This OR gate combines the results. If any one of the 3 AND gates outputs a 1, the OR gate will output 1, meaning the election result is yes. This is the complete gate-level circuit. It uses exactly 3 AND gates and 1 OR gate, a total of just 4 gates, to implement the entire majority voting function. Now let's look at how this circuit would be built using actual integrated circuit chips. We need 2 ICs. The first is the IC7408, which is a quad 2-input AND gate chip. This means it contains 4 AND gates inside a single 14-pin package. We will use 3 of the 4 available AND gates, 1 for A and B, 1 for A and C, and 1 for B and C. The second IC is the 7432, which is a quad 2-input OR gate chip. Since our design needs a 3-input OR, but each gate on the 7432 only has 2 inputs, we chain 2 OR gates together. The first OR gate combines the outputs of A and B and A and C. Then the second OR gate takes that result and combines it with the output of B and C. This effectively creates a 3-input OR function. Both chips require a 5-volt power supply connected to pin 14, which is VCC, and ground connected to pin 7, which is GND. The diagram shows all the pin-level connections, making it straightforward to wire this up on a breadboard or printed circuit board. Let me summarize the 6 design steps we followed to arrive at our final circuit. Step 1. Identify the inputs and output. We determined that there are 3 binary inputs, vote A, vote B, and vote C, and 1 binary output, the election result. Step 2. Construct the truth table. We listed all 8 possible input combinations and wrote down the expected output for each one based on the majority rule. Step 3. Derive the Boolean expression. We extracted the min-terms from the truth table rows where the result equals 1 and combined them using the OR operation to get result equals A and B or A and C or B and C. Step 4. Design the AND gates. We connected each pair of inputs to 3 separate 2-input AND gates. Step 5. Design the OR gate. We connected all 3 AND gate outputs to a single OR gate that produces the final result. Step 6. verify the circuit. We tested all 8 input combinations against the truth table to confirm that the circuit operates correctly for every possible scenario. These 6 steps form a systematic approach that can be applied to any combinational logic design problem. Here is a summary of all the components in our circuit. We use 3 AND gates, all from the IC7408 chip. AND gate 1 takes inputs A and B and produces A and B. AND gate 2 takes inputs A and C and produces A and C. AND gate 3 takes inputs B and C and produces B and C. We use one OR gate from the IC7432 chip. It takes the 3 AND gate outputs and produces the final result. That gives us a total of just 4 logic gates. This is the minimal gate count needed to implement the majority voting function. It's a very efficient design. In terms of physical hardware, you only need 2 integrated circuit chips, one 7408 and one 7432. Both are inexpensive, widely available, and easy to work with. This makes the design not only simple, but also cost-effective and practical for real-world implementation. And now, the conclusion. We have successfully designed a digital voting system using basic logic gates, AND gates, and OR gates to implement a majority voting function. The Boolean expression that drives our circuit is result equals A and B, or A and C, or B and C. This expression accurately implements the majority rule. Whenever at least 2 out of 3 voting stations vote yes, the output is yes. Otherwise, the output is no. The entire design requires only 4 logic gates, which can be built using just 2 standard integrated circuit chips, the IC7408 for AND operations and the IC7432 for OR operations. This makes it a simple, reliable, and cost-effective solution. Through this case study, we demonstrated a systematic approach to digital logic design, from defining the problem to constructing a truth table, to deriving the Boolean expression, to building and verifying the circuit. This same methodology can be applied to many other logic design challenges. Thank you for watching, and I hope this presentation has helped you understand how logic gates can be used to solve real-world problems.